In every elimination example we've had so far, we've been fortunate enough to have the coefficients of the variables be the same so that we could eliminate them by subtraction or addition. But what if we run into a situation where this isn't so, where the coefficients are different? Well, what we can do is we can find one of the variables where the coefficient is 1 in one of the equations and multiply it by a certain number so it matches the coefficient of the variable in the other equation. Now, this sounds a little confusing, just saying it as such, so let's look at some solid examples. Here we have two equations, x plus 3y equals 11, 3x plus 2y equals 19. None of the coefficients of either the x or the y match up. However, if we took that first equation, where the x has a coefficient of 1, and we multiplied it by 3, we would get this. 3x plus 9y equals 33. Now, if we bring in the second equation, now the x's both have a coefficient of 3. They're the same, so in this case we can use subtraction and eliminate the x variable. Doing that, we end up with a value of 2 for y. Now we're simply doing what we've done before, plugging that variable into one of our earlier equations to solve for the other variable. X ends up having a value of 5, so the solution to these particular two equations is 5, 2, with the accompanying graph. In this example, once again, neither of our variables have the same coefficient, but we look for the variable with a coefficient of 1. In this case, in the 2x plus y equals 7, the y has a coefficient of 1. And if we take that y with a coefficient of 1 and multiply it by 4, there's our first equation. Now the second equation, after being multiplied by 4, it too has a similar coefficient as the first one. So we have negative 4y and positive 4y. The signs are different, so we'll use addition to eliminate, giving us a result of 11x plus 0 equals 44, reducing with a value of 4 for x. Once again, now we just have to plug it back into one of the original equations to solve for y, and we end up with a value of negative 1 for y, so our point of intersection, or our solution, is 4, negative 1. A company hosted a winter holiday reception at a local banquet hall and served 2 different dinners. There were 200 people who attended the function. Let X represent the number of roast beef dinners, and Y represent the number of grilled chicken dinners. We're assuming everybody's eating. Therefore, the number of roast beef dinners plus the number of grilled chicken dinners will be 200. So x plus y will equal 200. There's our first equation. Now we're told the roast beef dinners cost $21 per plate, and the grilled chicken dinner costs $15 per plate. The dinner cost the company a total of $3,720. So the roast beef dinners, being represented by x, could be stated as 21x, and the chicken dinners, represented by y, each costing $15, could be represented by 15y. So 21x plus 15y will equal a total of $3,720. Now we have our two equations. X plus y equals 200. 21x plus 15y equals 3720. However, neither the x nor the y variables have the same coefficient. But if we take one of the variables from the first equation, they both have a coefficient of 1, so we could pick either one. But if we multiply the first equation by 15, we would get 15x plus 15y equals 3,000. The x's and y's now have the same coefficient, and they're both positive. So by using subtraction, we can eliminate the y variable, leaving us with a simpler equation of negative 6x equals negative 720, or 6x equals 720. X will have a value of 120, remembering that x is the number of roast beef dinners. So we'll plug that x back into one of the earlier equations to solve for y, and we end up with y having a value of 80, representing 80 chicken dinners. So our point of intersection is 120, 80, representing a scenario with 120 roast beef dinners and 80 chicken dinners being served.